Now we'll talk about some fundamental properties of probability. The first one says the probability of an event occurring is always a number between 0 and 1, and this is inclusive. So if an event has a probability of 0, that means that the event is impossible. If an event has a probability of 1, it means that it's certain and guaranteed to happen. And then you can have any fraction or any percent between 0 and 1 be a probability of something. Now in real life, we often have events that maybe have a probability of something like 0.99999, and we also may have events that have probabilities that are like 0.00000, a whole bunch of zeros, and then 1. And in real life, if something has a probability that's this low, we would generally consider it to have a probability of 0 just for real life purposes, even though weird things can happen. Same thing if something has a probability like this that's very, very close to 1 but isn't actually 1. So examples of something that might have a probability like this, if you've played Pokemon, the Master Ball's chances of success is a number very close to 1, but it's not actually 1. Master Ball can fail. And then other things that have very low probabilities, certain side effects on medications, but they have to mention it in the commercial anyway so they don't get sued. Winning the lottery is also something that has a very low probability. It might as well be 0, but you can look up what the actual probabilities are on, lottery websites. I think they legally have to tell you what probabilities are. Before we can talk about the next property of probability, we need to define what a complement is. So the complement of an event A, denoted with this tilde A, there are a few other ways that it can be written. It can also be written like this, A with a little c, can be written A with a bar over it. You might see this in other books. Our textbook, I believe, writes it like this, is the event or events that occur when A does not. So let's look at an example. Let's say our experiment is flipping one coin, and event A is landing on heads. The complement of A in this case would be landing on tails. If we don't land on heads, we have to land on tails. There's nothing else we could possibly land on. Now let's say our experiment is rolling one 6-sided die. Event A is landing on the face that has a 1 on it. The complement of A, in that case, would be landing on any of the other 5 faces. So it would be landing on 2, or 3, or 4, or 5, or 6. Any one of these 5 things could happen if we don't land on 1. So in this example, the complement is a collection of other events that could happen if this event doesn't happen. Now our next example, we roll one 6-sided die. Our event A is landing on 1, 2, or 3. A's complement would be landing on 4, 5, or 6. Now we can get to the second fundamental property of probability, which is the probability of A plus the probability of A complement is equal to 1. And this is always going to be true. Probability of A, that's how we would read this, plus the probability of A complement is equal to 1. Other ways this formula might be useful to us is if we rearrange it with algebra, we have 1 minus the probability of A is equal to probability of A complement. Sometimes this can be useful if we want to find the probability of something, but it's easier to find the probability of the complement. You just take 1 minus the probability of the complement, you have the probability of your event. Let's look at an example now. A bowl is filled with 20 pieces of candy, 3 of which are Smarties. If you close your eyes and pick a piece out at random, find the probability that the piece picked first is Smarties, and then B is not Smarties. So the probability that the piece is a Smarties should be 3 out of 20. That's because 20 is the total number of pieces of candy in the bowl, and 3 is the number of Smarties in the bowl. So that's our probability of getting a Smarties. Now they're asking us the probability that we pick a piece out at random and it's not Smarties. So this is actually the complement of the previous event, because if we want to find the probability of not getting a Smarties, that's every single thing that could happen except getting a Smarties. So one way we could find that is to do 1 minus 3 out of 20, which would be equal to 17 out of 20. So that's one way we can use the property to help us solve some problems. Like if they had just asked us B without asking us A, this is another way that it might be easier to solve. Let's see another example now. Here I would suggest pausing the video, try to work it out on your own, then hit play to see me go through the answer. Suppose a jar contains 10 marbles, 3 are blue, 2 are red, 5 are green. if we pick one marble out of the jar, what's the probability that it will not be red? So the probability that the marble will be red, we found before, that's easier to see. We can see that there's 2 red marbles out of 10 marbles total. The probability that it won't be red is equal to 1 minus the probability that it is red. It's going to be 1 minus 2 out of 10, which is equal to 8 out of 10. Another way we could have solved this is we could have said, okay, well, we're not getting red, so there's 3 blue that we could get, or we could get 5 green, and that gives us 8 things we could get, and then that's going to become 8 out of 10. So you don't necessarily need to use these properties to solve problems, but sometimes they do make things easier. Now we'll talk about the makeup of a standard deck of cards before we can get to some examples that involve playing cards. In a regular deck of cards, there's 52 cards in a deck. Forget everything you know about jokers. We don't use jokers in any examples we're going to be looking at. There are 2 colors in each deck. 26 of the cards are red, and 26 of the cards are black. Within each color, we have 4 suits. So among the red cards, you have 13 hearts and 13 diamonds. And among the black cards, you have 13 clubs and 13 spades. Then within each suit, you have 1 of each. 2, 3, 4, 5, 6, 7, 8, 9, jacks, queens, kings, and aces. Jack, queens, and kings are also referred to as face cards. So sometimes you might see a problem asking you about the probability of getting a face card. That means they're talking about these 3 cards specifically. So now let's look at some examples. Suppose one card is drawn at random from a standard 52 card deck. Find the probability that the card drawn will be first a spade, then not a spade, then a jack, then a spade and a jack. So we know that there are 13 spades in the deck, and there are 52 cards in the deck total, so a probability of getting a spade would be 13 out of 52. Another way we could have thought of this, or if we reduce the fraction, we'll see it's also equal to 1 over 4, where we could say 4 is the number of suits, and 1 is the number of suits that are spades. Now for part B, we want to find the probability we select a card at random, and it's not a spade, and this is one where it's easy to use the facts that we know about complements instead of adding up all of the other suits. So we could do 1 minus 13 over 52, or 1 minus the probability that we do get a spade, and we end up with 39 over 52, which also simplifies to 3 over 4. For part C, we have 4 jacks in the deck, so our probability here would be 4 out of 52. Part D, we want to find the probability of getting a spade and a jack. There's only 1 card like this. So the jack of spades is the only card that's both a spade and a jack. We have 13 spades and we have 4 jacks, but only 1 card is both a spade and a jack, so our probability of getting a card that's a spade and a jack would be 1 out of 52.